2, 1, 3. 6 arrangements total. What's the very next bigger one? Stick around. The trick behind this answer runs inside every combination lock and scheduling system you've ever used. A boy has to slice a chocolate bar into 3 equal sized pieces using vertical and horizontal cuts. And you need to figure out the minimum number of cuts required. Or say it's impossible if the bar can't be split that way. You're given the bar's height and width, and the answer should just be that minimum cut count. Wait, that doesn't match. Let me redo this for the actual problem given. You're given 2 strings of the same length made up of lowercase letters, where one is the string you have and the other is a target you need to beat. The task is to rearrange the letters of your string into the smallest possible version that still counts as coming strictly after the target when compared alphabetically. If there's no way to rearrange the letters to beat the target, you should say so by returning nothing. This one's called Lexicographically smallest permutation greater than target. I'm Kai, and this is Fun with Learning Technology. Let's get into it. Think of it like a bike combination lock. You've got a fixed set of digit wheels you can spin into any order, and you're trying to beat a specific combo someone else set. Here, our wheels are the letters in S, and the combo to beat is target, both lowercase, same length. We rearrange S any way we like, and target never moves. We need the smallest rearrangement of S that's strictly bigger than target. If nothing we can build beats it, we return an empty string. Take S as ABZ and target as BBA. Line up every arrangement of ABZ, ABZ, AG, BBA, BCAB, ZBA. Only BCA, CAB, ZBA are actually bigger than BBA. The smallest one in that surviving group is BCA. That's our answer. Length only goes up to 300, so we don't need anything exotic. But it also rules out generating every permutation, since that number explodes fast. And since we're stuck with just 26 lowercase letters, checking is there a bigger letter available is always a tiny fixed size search. The obvious idea, list every permutation, sort them, then pick the next one. For 3 digits, that's fine, 6 options. But for 10 digits, that's over 3 million permutations just to find one answer. Instead, look at the digits from right to left. As long as each digit is bigger than the one after it, that suffix is already maxed out. It can't be rearranged into anything bigger. The moment we find a digit smaller than something to its right, we found our pivot. The one spot we can actually change. Now we need to bump the pivot up. But only just barely. Look at everything to the right of the pivot and find the smallest digit that's still bigger than it. Swapping in the smallest possible bigger digit keeps the result as close to the original number as we can get. After the swap, the digits after the pivot are still in decreasing order, the largest possible arrangement. But we want the smallest arrangement, so we reverse that entire tail. Now those digits count up instead of down, giving the least value there. Let's actually run it. We start one step before the end and walk backward as long as each digit is bigger than or equal to the one after it. On 1, 2, 4, 3, that stops right at index 1, because 2 is smaller than 4. That index 1 is our pivot. What if the digits are already in the biggest possible order like 3, 2, 1? Scanning right to left, we never find a smaller digit before a bigger one. That means there is no next permutation at all. We've hit the ceiling. This exact pivot, swap reverse routine, is what the C++ standard library's next permutation function runs under the hood. It shows up anywhere a system needs to step through every possible ordering, one at a time. Scheduling, key orderings, combinatorial search, without ever holding all of them in memory at once. Back to 2, 1, 3, the pivot is the 1, because 3 comes after it and is bigger. The smallest digit to its right that's still bigger is 3. Swap them, giving 2, 3, 1. Reverse the tail after the pivot and the answer is 2, 3, 1. The very next permutation found in one linear pass. Here's the catch. Target isn't just S shuffled. It can have completely different letters in different amounts. So we can't scan target's own layout for a pivot like before. Think of it like an IOU tally. At each position we ask, do we still have enough of the right letters left in stock to even match target this far? We keep a running count of shortfalls. Go negative on a letter. And that prefix isn't buildable yet. Let's type this out from the top. We import counter since we only ever care about how many of each letter we have, not their order. We grab the length and count every letter in S. Then, before the main loop even starts, We pretend to use target's letters for everything except its very last character, subtracting them out one at a time, and any time a letter's count dips below 0, we bump a counter called neg, which just tracks how many letters we are currently short on. Now the real loop, we walk position I backward from the end. If neg is 0, that means everything before this position is actually billable from S. So we search upward from target's letter at this spot, letter by letter. For the first one we actually have spare. The moment we find one we use it, then dump every remaining letter we are holding, smallest to biggest, right after it, and return the whole string immediately. If neg isn't 0, or if no bigger letter was available, we don't build anything here. We just put target's previous letter back into account, since the next loop step tries a shorter prefix, and if that letter had been one of our shortfalls, we shrink neg back down. If we walk all the way through without ever returning, there is genuinely no permutation of S that beats target, so we return an empty string. The neg counter is doing the job the pivot scan did earlier. It's just checking whether this prefix is even possible before we bother searching. The inner loop over letters is exactly the find the smallest bigger one step from before, just applied to a count of letters instead of a fixed layout of digits. Each position does at most a fixed 26 letter check, so the whole thing runs in time proportional to the length of the strings, with only a small constant amount of extra space for the letter counts. The pattern underneath, find the last spot you can still improve, swap in the smallest valid upgrade, then minimize everything after it, shows up anytime you need the next best arrangement without listing every possibility. Same idea, different data. Talk is cheap. Let's actually run this. I fed it all 3 of the problem's real examples, no cherry picking plus 3 extra edge cases I picked myself. Let's actually time both on a real 10 element input. Brute force took 2.39 seconds. The optimal version took 36 microseconds. That's a real 6 fib seconds by 2.4x. From actually running both just now, not a complexity estimate. Quick one for you. Once you pick the swap position, which digit from the tail do you actually swap in and why? Pause here and think it through. Think about what makes that tail special once you've sorted it. You pick the smallest tail digit that's still bigger than the pivot. Since the tail is sorted, that swap gives you the smallest possible jump upward. Second one, after swapping in the new pivot digit, what do you do with the rest of the tail? And what does that operation cost you? There's one cheap operation left that guarantees you the smallest possible answer. You just sort the remaining tail ascending. That's the smallest arrangement possible, and it only costs you a log n sort on top of the linear scan. This problem asked for the smallest permutation strictly greater than the target. The classic next permutation pattern. The trick is finding the lightmost ascending break, swapping in the smallest valid replacement, then sorting the tail. That avoids generating all permutations, so it runs in on time instead of on.